All right, so good evening, everyone. So as Intamam said, I am presenting a paper called An Adaptive Approach on Credit Card Fraud Detection Using Transaction Aggregation and Word Embeddings. And it was written by Yesel Kanad et al. And it was presented at the IFIP International Conference on Artificial Intelligence Applications and Innovations 2020. So for the talk today, I'll first give an introduction into the problem area. Then I'll talk about the proposed fraud detection system, the experiments that they used to test their system, as well as the main points from the paper. So due to the large surge of interest in online retailing, especially now with COVID and more people are moving their businesses online, there is a rise in the use of credit cards online. So according to the fifth report of the Single European Payments Area, a report in 2016, the total value of fraudulent transactions was 1.8 billion euros. And 73% of this came from card not present transactions. And in comparison to ATM fraud and point of sale fraud, credit card fraud increased the most over the 4-year period, and it increased by 2.1%. And the authors presented some problems that you can encounter when developing a fraud detection model. So they said that when selecting the training set from hundreds of millions of imbalanced transactions, these can be problematic, as well as the selection of the most appropriate feature combination, because the features that between the fraud and non-fraud transactions are indistinguishable. Also, there's the skewness of the data and the cost of false positive samples, and also the durability of the model to address variance in trends. And this is known as concept drift. So this comes about because of changes of behavior, not only with the fraudsters, but also with the customers as well. So with imbalanced data is when you have unequal distribution of both classes in your data sets, or if it's more classes than among the classes. With fraudulent data, it is highly imbalanced. So there are much fewer cases of fraud than legitimate instances in the data set. So the author said that using resampling approaches, which is normally used to deal with imbalanced data, may be problematic with credit card data because the credit card data is so highly imbalanced. So they introduced a card-based equalization method that uses both fraud and non-fraud cards in order to generate the training data set, which incorporates all transactions of the sample cards. So the properties of fraudulent transactions alter over time, and this is mainly due to the fact that fraudsters try to bypass the fraud detection systems. Also, because of purchasing trends that vary over time in these online markets, you also have those properties varying, and these shifts in trends are again known as concept drift. And this is when you have the distribution of the data stream not being stationary. And conventional fraud detection systems may not be suitable for this type of data because they may not be able to adapt to these concept drifts. So the authors propose a system that can retrain itself over time, and they also introduce a sliding window-based automated training dataset generation technique to deal with this concept drift issue. So transactions well, credit card transactions are performed from various sources known as terminals. And these terminals transfer data to the owner bank of the credit card, and they do so in ISO 8538 standard. And the data is structural and in standardized format. But sometimes for some of the attributes, the data is not sent correctly, and this can be problematic. So for example, the example shown there is Facebook spelled 2 different ways. So the author's way of addressing this issue is using character level word embedding, and they map the merchant name to a vector of real numbers. And by doing this, they made the merchant name a more distinctive feature for the credit card fraud detection. Online transactions are real-time events. So the detection of whether a transaction is fraudulent or not needs to be done in milliseconds. So in order to provide a fast and reliable solution, the authors used a gradient boosting tree approach. And this was developed with different types of features. So numeric, handcrafted, numeric, categorical, and textual features. So the proposed fraud detection system, it comprises of both an online training model and a real-time detection model. And both of these contain a feature engineering component. For the offline training, there is automatic generation of the training set, which is used for the generation of the fraud detection model. And in the real-time detection, the feature vector is formed for the streaming transaction in order to detect it as fraud or not. The feature engineering component of the models intends to address the high imbalance of the data, or the high class imbalance, as well as noisy labels and features, and also overlapping transactions of both classes. And they do so by employing some methods. So these are listed here. So by combining the different types of features, also the selection of among the distinctive features, and the generation of the additional handcrafted features. So figure 2 shows an overview of the feature engineering process. So to form the combination of features, first the categorical values are encoded, and the aggregated features are also created. Also, word representations are made from the textual data, and the feature vector from the merchant name is used or is combined with other features in the offline training model in order to provide the training set for that model. And it is used or queried in the real-time detection model in order to determine something is fraud or not. For the categorical features, these are encoded into a distinct number of numerical features. So the numbers range from 0 to K, where K is the number of categories in the feature. So these type of features include the merchant category code and the country code. In order to capture purchasing patterns, and aggregation strategies apply to the raw transactional features such as the amount or the currency. And in order to try to predict a customer's behavior, the authors define a predefined time window in order to select previous transactions to be used for that prediction. And the time window that they selected for their experiments was 1 day. So they take the previous transactions and create aggregated features such as number of transactions in the time period, or number of transactions with the same currency, or number of transactions. A number of transactions with the same merchant code. And all of these features are computed in real time. For the word embedded model, the merchant name is a textual field and it comprises of millions of different values. So these can include meaningless words or even phrases of varying lengths of characters. So using an encoding that you would typically use for categorical variable would not work for merchant name. And the list of these merchant name grows as you get new merchants and also when you mistype the name of a merchant. And this brings about the problem called out of vocabulary problem. So to address this, the authors wanted to create a feature vector for the merchant name. So to do that, they used a fast text library, and this provides a character level word embedded. So it had an embedded vector for the merchant name and trigram character sequences of all the unique names of the merchants that appeared in at least one transaction and contained only alphabetical characters were considered for the model. And the embedded model was trained on a corpus with millions of these filtered unique names. And it created a 16-dimensional embedded vector for the merchant names. And for an incoming transaction, the vector is computed by summing all the vectors extracted for each trigram sequence in the name. Because of the time restriction that you have with credit card fraud detection, the FastX model is not retrained. So this includes not being retrained with new merchants. And the feature vector for that merchant name, when it is combined with other features from the dataset, it may dominate the other features. So in order to address this, the authors use principal component analysis to extract the more distinct features and also to reduce the dimensionality. So the technique removes the correlation and preserves the orthogonality between the word representations. So the PCA method projects the 16-dimensional vector onto a 4D subspace. So by reducing the dimensionality, it reduces the dominancy of the merchant feature vector on the other transactional features. And the authors also found that by doing this, the performance and also prediction time of the model increased. Figure 3 just shows an illustration of the embedding vectors projected onto 2D space. And this is generated on a set of merchant names in the training set. And in order to train the credit card fraud detection model, the training data was constructed in a series of stages in order to try to reduce the skewness of the data. The credit cards were characterized as fraudulent or legitimate. So if a credit card appeared in at least one transaction that was fraudulent, it was classed as fraudulent, otherwise it was classed as legitimate. And the authors selected equal numbers of training instances for fraud and non-fraud transactions. And the training set was constructed in a period of T with M number of consecutive months. So this is illustrated a little better in the diagram. So you have that time range T, and in this example, they use 10 months for the value of M. And the last set of C months are the card selection zone, and the beginning set of B months is the transaction buffer zone. And for each time period Ti, if you have K fraud cards in that time period, then K legit transactions with K legit cards are also selected for that time period, and this was their way of balancing the data set. So for a time period Ti, the cards in the transactions for that time period as sampled from the range Ti minus n, and n is the sliding window parameter. So for the experiments, the authors obtained their data set from a private bank, and they had two sets of training and test sets. The first training data comprised of transactions between October 2018 to July 2019. The test data was August 2019. For the second set, the transactions were from November 2018 to August 2019, and the test set was September 2019. And 30% of the training data was used for validation. And in order to develop their model, they used Python 3.6.8, XGBoost Library 0.71, and they also used Redis for real-time transaction aggregation. Table 1 shows an overview of the statistics of both the training and test sets. So it shows the number of transactions, number of cards, number of fraudulent transactions, and number of fraudulent cards. So you can see it there for both training sets and both test sets. The evaluation metrics used by the authors were false positive rate, recall, precision, area under the curve, and the equal error rate, which was the threshold values for false acceptance rate and false rejection rate when both rates were equal. In table 2 and 3, they present the success measurement results of the fraud detection system. So table 2 is for the first set of training and test data, and table 3 is for the second set. And for both the features, they compared the system, how it worked with just the encoded features, also the aggregated plus encoded, and then the embedded plus aggregated plus encoded. And if you look at table 2, you'll see that the area under the curve increased as the number of features increased. They also find that using a fixed false positive rate of 0.3 gave good results. So they use that in order to get a value for recall. And you can see that there's a higher value for recall with the 3 sets of features. And in the equal error rate section, the recall increases as the number of features increases, and also the error decreases as the number of features increases. Similar trends are seen in table 3. So experiments were also done on automated training sets. So these were generated using the sliding window approach, and it was formed, the data sets were formed using the 2 training data sets. So that's the data sets between October 2018 and July 2019, and also November 2018 and August 2019. And for each of these data sets, a brand new gradient boosting tree model was trained, and the detection performance were evaluated on the same test set, and the test set they used was September 2019. So the graph here shows the recall against false positive rate, and this one shows it for the first set of testing. So it's with the encoded features, aggregated and encoded features, and the embedded plus aggregated and encoded features. And they have it there for the 2 different test sets. And you could see that the better performance with the 3 sets of features. In figure 6, this shows the results of recall versus false positive rate for the 2 different data sets when using the sliding window approach. And from this graph and also this table, table 4, they found that using the sliding window approach increased the area under the curve by 0.028% and recall by 0.029%. And they said that using more recent transactions for the predictions gave more accurate results than using transactions that were further in the past. So in conclusion, the authors proposed a way to construct a training data set from different types of attributes such as numerical, handcrafted numerical, categorical, and textual features. They also introduced a character level word embedding method, and they used this to embed their merchant name into a vector. And they also used had a transaction data set that was developed to extract feature vectors used as training set to generate a gradient boosting tree model. And for future work, they suggested that they would try using new aggregated features, as well as an ensemble method with various models, and train using long and short-term periods. Right, so that's the end of the presentation, and this is the reference to the paper. Any questions?
Yeah, can you just go back to the last table you had there?
Yeah.
So this is saying with the training set going up to July, you got better performance than the more recent training set?
I think this is an error in their paper. I just presented it as they have it, but I think it's supposed to be the opposite because they said they got an increase with the more latest data, and the more latest data is the one that ends in August. So
Okay.
I think there's an error in their paper.
Okay.
On the graph.
Yeah, go ahead.
Yeah, the graph shows it there as well. So.
Okay. Okay. Yeah. So with the work you are doing right now, are you using any of this stuff, or you tried any of it, like the sliding window?
Not with the sliding window, but with the time periods. So I'm using, well, it's something like a time period, in a sliding window using different folds with different periods in time, and then testing it against data that comes right after it. So I guess it's sliding window kind of approach.
Okay, okay.
But yeah, not exactly the same way that they did it.
And the other thing is, so the training set will be updated, periodically. And I think you said they used the most recent 10 months, right? That was the window they use for training set.
Oh, that was just an example. They use
just okay.
Process, yeah.
Because I guess there's a trade-off there, right? And so the question is it possible to use different periods for different features? I don't know how you would do that, because some features won't change very often, right? So you might as well keep a longer period for those, but I'm not sure how you would combine, yeah, it'll be difficult.
Well, for mine, from the discussions, I was told that when you pull the data, you don't always get back the same set of features, but they're generally, from the data sets that I got, some main features that are consistent. And they also said that if it's a problem, then they would have to contact the people who's in charge of that system where they pull the data from, to try to get more consistent features.
Okay, all right.
It was a discussion, yeah.
All right, yeah, thanks, Shellyann.
No problem. Any other questions?
I have one question.
Yeah.
Yeah, and with the corpus that they used, it seems like they're trying to, in trying to get these embeddings, they're like trying to sort of like it's like an entity they're trying to identify identities. So did they like augment, did they like, for instance, you have Facebook proper spelling, they showed the example of face B. So did they like do any sort of work to sort of artificially create spelling errors, for instance, and sort of enrich the training set? So they said it was like 1 million plus
Yeah, I did.
corpus. The word corpus that they use was like about 1 million plus. So do you know if they like would have looked at like using just sort of like creating new examples of the potential spelling errors that they would see, or they see, for instance?
They had to create it, so I assume they just used what was existing in the data set that they had. So they didn't say anything, creating their own.
Okay.
But because it was a large data set, I guess they had enough examples.